Here we're going to look at question 13 from section 2 of the ENGAA specimen paper. So in this question we're told that we have two identical springs, each with a spring constant K and a natural length L of 12 centimetres. We're told that we take these two springs and attach them together with a 100 gram mass at the point where the two springs connect and a 100 gram mass at the very bottom of the two springs, and that they're hung from the ceiling, and that their total length in this case is going to be 30 centimetres, not including the lengths of these 100 gram masses. So what the question asks us to do with this information is to find K, the spring constant of each of our springs. So if you'd like to have a go at this question yourself, then just please pause the video now. Otherwise, let's have a go at it together. So to go about answering this question, there's a few different ways in which you can do it, but what they're all going to use is a similar law which is true for all springs, and that is Hooke's law, that the force that a spring is undergoing is equal to the spring constant multiplied by the extension. So what we can try and think about is how we can apply this law to the springs in this case. So what we could do, for example, is we could think about the force on each spring and the extension of each spring, and then use that to find our spring constant K for each. Now, since we're going to need extensions, let's try and think about the information we've been given relating to extensions. So we've been told that the total length, the natural length of each is 12 centimetres, and that in total this is stretched out to 30 centimetres. So the total extension is just going to be 30 take away this 24 from the total natural length of the springs, to give us a total extension of 6 centimetres. Now this is the total extension and not the extension of each of the springs, so it's not straight away useful, but it will come in handy, as we should hopefully see in a moment. But before thinking any further about the extensions, let's think about the forces acting on our springs. So what each spring is going to be doing is pulling up the weight beneath it that it's holding up, for example. So we can label these forces on here, with F1 being the force for our first spring here, labelled 1, and F2 being the force for our second spring. Since our first spring is holding up this 100 gram mass plus the 100 gram mass here at the bottom, the total force it's holding up is going to be 0.1 G, where G here is representing the gravitational field strength rather than grams, giving us a total force of 0.2 G being held up by spring 1. When we go ahead and look at spring 2, then the force is going to be 0.1 G, since it's only holding up this single force down here at the bottom of this spring. So with this, we now have the forces acting on each of the springs, which we could substitute into Hooke's law. But to do that, we would need the extension of each spring. So let's see if we can find the extensions of them using our total extension here of 6 centimetres. Now, since Hooke's law is linear, we might expect that since this one has 2 times the force of this one, then we can work out the total extension from this, since it's going to just be proportional due to the linearity of Hooke's law. So what we can do is we can say that for this first spring, the extension is just going to be proportional to the fraction of the force divided by the total force that the springs are going through. So since it's holding up 0.2 G of the total weight of 0.3 G, this is going to be 2/3 of this extension of 6 centimetres. So the extension of spring 1 is going to be 4 centimetres. Doing the same thing for spring 2, we can just tell that proportionally this is going to be 1/3 of our 6 centimetres, or our remaining 2 centimetres, making our total extension just 6 centimetres. So now that we have these two extensions and these two forces, all we have to do is substitute them into Hooke's law to get our spring constant. So going on to the next page, we can keep our forces up here and our extensions, and since we know that the spring constant is the same for both of our springs, then all we have to do is to use Hooke's law for one of them. So we could take our first spring, for example, and substitute in our force of 0.2 G equal to our spring constant K multiplied by our extension of 4 centimetres. Then rearranging, we get that K equals 2 divided by our 4 centimetres, so K equals 0.5 newtons per centimetre. Now if we were to do this with our second spring as well, we would get exactly the same answer, hopefully sort of reinforcing that our answer is correct. And this is going to be our final answer, which just corresponds to answer E given in the question.